Yeah, good morning. I'm here, Srimati, taking CSE 1003 Digital Logic Design in G1 slot. I said about the textbook in the last class, which you have to follow is as per the syllabus is Digital Logic Design by Maurice Mano and Michael D. Seletti. Module 1 covers number system, base conversion and binary codes. You have just seen the binary systems before number system. Before going into number system, there are two types of electronic circuit. Why we are going in for digital as well as digital circuits? As there are two basic electronic circuits. They are analog circuits and digital circuits. Analog quantities are continuous with respect to time, and they are they normal in day-to-day life. Whichever we encounter is the temperature, pressure, sound, and voltage. And the advantage of digital quantities are you can digital quantities means you will be having discrete values with respect to time. You will be having discrete values of whatever that we are measuring with respect to time, that will be having discrete value. It won't be continuous with respect to time. And those discrete values may be of only two values, either 0 and 1. They are said to be binary, 0 and 1, and they are transmitted, they can be transmitted easily and efficiently. And if we store data in terms of 0 and 1, the storage will be compact, and as like your analog signal, your digital signal won't be affected by your external noise. Your analog signal will be affected like this. So normal nature of the signal will be tilted, or it will be affected, so the data will be also affected. And coming to your analog and digital, as I said already, analog signal will be continuous with respect to time, and digital signal will be discrete with respect to time. And coming to your digital electronics, it will be having only two possible values. You can store the data in terms of two possible values, either in 0 or in 1. And those values are in terms of if I am designing a circuit, if I need to give a logic 1, I will be giving in terms of voltages. So the 1 will be representing high voltage level, that will be in the range of 2 to 3.3 volts, and 0 will be in the range of low voltage level, that usually I will give it as 0 to 0.8 volts. And when I am giving see both 0 and 1, I am giving the value 0 and above 0, so that is said to be positive logic. And combination of these zeros and ones is said to be codes. And you will be representing your symbols, alphanumeric characters, numbers, everything in codes by using codes. And digital systems, it involves two types of waveforms. One is periodic and aperiodic. Periodic will be like your on and off time, or the total period t will be repetitive, like your on and off time, the total t won't be varying for n number of cycles. That is said to be periodic waveform. Aperiodic is not like that. Each cycle will be different. That is said to be periodic waveform. Why aperiodic waveform? Why we are going ahead with this waveform is if we are designing a digital circuit, as human being or synchronized with respect to clock, and we are working with respect to our own 24 hours clock, the digital system will also have its own clock. When a digital system is working with respect to clock, whatever operation that we are asking the digital system to perform, all those operations will be synchronized with its own clock. So those type of digital circuit is said to be sequential circuit. Those type of digital circuit is said to be sequential circuit. And with respect to clock, all the operations, namely for example, if I am going to add A and B, this is your clock. The A data will be present for one period of time, and the B data will be present in another period of time, the same period of time. Only then we can add 1 plus 0, and the resultant will be 1. Let it be C. That can be done by using an OR gate, for example, I am telling. And coming to your data transfer, you can serially transfer a data in terms of zeros and 1, meaning only one bit can be transferred from the sending end to the receiving end, whereas parallel data transfer, you can parallelly transfer multiple bits of data from the sending end to the receiving end. A number system, there are basically four types of number system, namely decimal, binary, octal and hexadecimal. And decimal, the radix is 10, and binary, the radix is 2, and the octal, the radix is 8, and the hexadecimal, the radix is 16. And we have seen how and all these number systems are weighted number system, namely the first number system, the decimal number system is a weighted number system. Each position of the digit is given a weight, that we know already from schooling would have read, that is unit, tens, hundreds, the normal decimal number, that is how we will be representing. So weighted number system, each position of the number in a given number, each position of the digit in a given number will be given a weight. And usually how we will be converting a normal decimal number to a binary number is by repetitive division method, and if you go ahead with this number, and before your decimal point it will be 0, 1, it will be 10 to the, because the radix of the decimal number is 10, so 10 power 0, 10 power 1, 10 power 2, 10 power 3, it goes on and on. And similarly to the right side of your point, decimal point, it will be 10 power minus 1, minus 2, and so on. Okay. And if I need to convert decimal number to a binary number, we have converted, we need to divide a decimal number by 2, and then we have to go ahead with that. And but for the decimal point, this is how I said about the decimal number. And the binary system, binary number will be represented by zeros and 1, a radix of base is 2, and we have only 2 digits for a binary, either 0 or 1, and 1 is otherwise called as on, true, high, and s, whereas 0 is called as off, false, low, and no. And if I need to convert a decimal number to the binary number, as I already said, I need to divide it by 2, and then I have to write it in this way as represented by the arrowhead. That is how I am representing a decimal number 0 to 1. A combination of 4 bits is said to be nibble, with a nibble from 0 0 to all 1, and 8 bits combination is said to be a byte. Okay. And octal number system, base 8. So from a decimal number, if I need to convert an octal number system, that you need to divide it by 8, and then again in the same way as represented by the arrowhead, we need to write the number. Okay. And hexadecimal number system also, it is nothing but the radix or base is 16, so we need to give a divide the given decimal number by 16, and then we have to go ahead with the same procedure as like your binary and your octal. And we have done a simple example yesterday, how to convert 36.49 to the base 10 to the base 10 in terms of binary, octal, and your hexadecimal Okay. And now how to convert this, let me take a binary to octal. So I am taking 100.011. Okay. So convert binary to decimal. Okay. So 100.011 to the base 2. Is it okay now? So now this is 100.01112. So if I write it, this is, since your base or radix is 2, this is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, and 2 power 5. And this will be 2 power minus 1, 2 power minus 2, 2 power minus 3, and 2 power minus 4. So if I take it, let me take this one first. Okay. So 0 into 2 power 0. Okay. And then 0 into 2 power 1. 1 into 2 power 2. 0 into 2 power 5. 0 into 2, I think this is 3. This is 3, this is 4. And 1 into 2 power 5. Please add this. Tell me the value. 2 power 0 is 1. 1 into 0, 0, 0. This is 4. And this is 0. This is 0. What is 2 power 5? 30, 32. So this is 32. So if I sum it up, 32 it is 36. Okay. And coming to your decimal point, again 0.0111. So it is 0 into 2 power minus 1, 1 into 2 power minus 2, 1 into 2 power minus 3, and again 1 into 2 power minus 4. Please add it up and tell me the answer quickly. So 2 power 0 into 2 power minus 1 into 0, somehow it is 0, and 2 power minus 2 is 0.25, and 2 power minus 3 is 0.125, and 2 power minus 4 is 0.0625. If I add this, 0.125 plus 0.25, I'll be getting if I add this, I'll be getting 0.4375. Yeah. So the total result is 36.4375. This is in terms of decimal. Approximately, closely we'll be getting. Oh, I'm sorry. This one. Okay. Because we have stopped up to 4 decimal points. You're getting me, guys? You're getting me? Yeah. So the same thing. Please do your conversion and tell me the answers quickly. Let me give different number. Yesterday we have converted a decimal number to other number. Now convert this 1101 to decimal, and then 236 octal to decimal, and CB hexadecimal to decimal. Convert and tell me the answers. See, the 1101 and 1101 number, I am writing it here. If I am combining 3 digits, that will form octal. Okay, so 2 power 3, that will be 8, because octal radix or base is 8, right? And if I combine 4 digits, that is said to be hexadecimal. That is said to be hexadecimal. So this is octal conversion, and this is hexadecimal conversion, and 101 and 011 and 11. So if I go back, octal 101, what is 101 is 5, and then what is the next 3 digit? 101 is 5, and then 011 will be 3, and again 11 is 3. Am I right or not? Yeah. if this, consider this as a binary, okay. Tell me the equivalent value of for this number, octal. 221 to either 221 to 8 or 1101 to 8. Tell me, use your calculator and tell me the answer. 2 to 1, convert that to octal, so that is 335. Yeah, see guys, look this binary, okay, binary. If I combine 3 bits at a time, okay, because what is the base of octal? It is 8. 8 can be written as 2 power 3, am I right? So the base for the binary is binary number is 2. So if I am combining 3 digits of a binary, that will become an octal. If I am combining 4 digits of a binary, that will become an hexadecimal. Okay, so now I have combined here 3 numbers. See, first 101 and then 011 and then 11. From the octal table you can just go through. Just now I have shown you the octal table. So I have to see 011, it will be from 0 to 8, 0 to 8 till 0 to 8, 7, meaning first 8 number will be same as like your binary number. Binary and octal there will be same 7, okay. After 8 only the binary and the decimal, and the binary and the octal. Otherwise I can say, see, the decimal is varying, you are getting me. 8 of decimal will be equivalent to 10 of octal. You getting me, guys? Till your 7 of decimal, octal and decimal number is same. Okay. The first thing is 101. 101 is 5, and then 011 is 3, and again 11 is also representing 3. So when I come back here, if you remember your table, so 101 is 5. Am I right, guys? 011 is 3 and 11 is again 3. That is what I have written here, and whichever you have said this. Is it clear what I am telling? And then one more thing. If now let me combine 4 digits. Okay. Let me combine 4 digits now. If I combine 4 digits, so this is 1101 and 1101. What is 1101? I think D. Am I right? Hex binary 1101. Your hex is D. So this will be D and D. Convert this into the other thing and tell me what is this equivalent to in terms of hexadecimal. Make your conversion, use your conversion and tell me the answers. Am I right? Guys? Yeah. So keep in mind, for in a binary, if I am combining 3 digits, that becomes an octal, and if we are combining 4 digits, that becomes an hexadecimal. Is that fine? This we have done, am I right? Okay, this we have done. And then will you convert this 359 decimal to hexadecimal and binary and tell me the answer. Answers, please. Okay, and then now I am going to say about your complements. Okay. So we have generally two type of numbers. One is said to be the sign number, and another one is said to be unsigned number. Okay. The sign number, for example, the 25 decimals equivalent is 11001. It is if I am representing a number 25 decimal, it is 11001. Okay. So, and as I said already, we will be writing any number as a combination of 8 bits. Okay, 8 bits as a combination of 8 bits. 8 bits is said to be a byte, and 4 bits is said to be a nibble. So, a byte will be having 2 nibble. A byte will be having 2 nibble. So, when MSB is 0, the most significant bit, see this is 1, 2, 3, 4, 5 is 20, only 5 digits we will be having for 25. I'll be, if I want to represent this 25 as a byte, I'll be adding preceding zeros other than your 11001. I'll be adding preceding 3 digits, because totally put together it's an 8 bit and it's a byte, or we will be having a combination of 2 nibble. And this number, the position, this number, how will I be numbering is 0, 1, 2, 3, 4, 5, 6 and 7. Okay, this is how I will be numbering a digit. This is how I will be numbering a digit. This is your LSB and this will be your MSB. This is your LSB and this will be your MSB. So, the most significant bit, okay, for a signed number, the most significant bit will be used for representing a signed number. If it is positive number, if it is plus 25, signed number means you will be using sign. Okay. For example, plus or minus 25 decimal. If it is 25 decimal plus, this will be, the most significant bit will be 1. Okay, the most significant bit will be 1. If it is an unsigned number, we won't be bothering about this most significant bit. For a signed number, if I want to represent a plus 25 number, the most significant bit will be 0, and if I want to represent minus 25d, the most significant bit will be 1, indicating us the whatever being the representation, that is your sign number. So, the plus 25d will be represented, this is plus 25d, whereas negative 25d will be represented as 100, 11001. This is how we will be representing minus 25d. See, I have written here. Okay, this form of representing a negative number is said to be sign magnitude form. This form of representing a number is said to be signed magnitude form. And we have two types of complements. One is said to be, okay, we have two types of complement. One is said to be r's complement, and another one is said to be r minus 1's complement. If it's a binary number, if this r is nothing but the radix, so mostly we will be using the radix 2 or radix 10, which is nothing but your binary and the decimal number. Because decimal number is a human way of representing a number, a binary number is nothing but machine language number. So, the 2's and 1's complement in case of radix r, if r is 2, so this will be 2 and this will be 1. Where we will be using this complement is, complement will be used for subtracting numbers. Okay, complements will be used for subtracting numbers. So, for subtraction of a number, for example, if we need to write a program for subtracting a number, human being will know in terms of decimal, the machine will know in terms of binary. And so, this is 2's complement and 1's complement, whereas in terms of radix 10, this is 10's complement and 9's complement. Okay, and how we will be taking it is, let me, as I said already, let me go ahead with 1's and the 2's complement. I am currently with slide number 38. Right. How will you represent 19 plus 19 in binary? Quickly tell me your answers. 19 decimal 10011 10011. So preceding 0, this will be the representation in terms of byte. Okay, this is your plus 19 representation, and 1's complement is nothing but, okay, 1's complement is nothing but what I'll do is all this bit I'll invert. 1 1 1 0 1 1 0 0. This is 1's complement of 19. Okay, and 2's complement is nothing but, after converting this 1's complement, I'll be adding 1. This will be 2's complement. 1 0 plus 1 1 0 1 1 0 1 1 1. This is 19 decimals 2's complement. Okay, this is 19 decimal 2's complement, and moreover this is plus 19. How will you represent minus 19? Your MSB will be 1. So this will be 1 0 0 1 0 0 1 1. This representation is said to be signed magnitude representation. You are getting me, guys? Right. So in the same way, this is your 21 is 1001101. Yeah. Usually this negative number will be represented as, this is minus 19. This is minus 19D. Use your calculator and check for your minus 19. For your decimal, minus 19 will be represented in binary. Is it right? Guys, please check. Use your calculator. As of now, you forget about this. The most significant number will be used for representing your negative number. Minus 19 will be represented by 2's complement. Only in sign magnitude form you will be making this most significant bit as 1. Okay, in complement form this will be the answer. In calculator you will be having 2's complement in this way. Check in your calculator, you are getting the correct answer. Check in your calculator, you are getting your correct answer. Yeah. So again, let me go ahead with 30. Okay. So 30 and minus 30. So 30 is binary. Will you please tell me 30 is binary? Four one zero, no, 1110, so 000. Huh? So minus 30, how will you represent in 2's complement? How will we representing in 2's complement? First, what is the procedure? Step 1, invert all zeros to 1 and ones to 0. So this will be, quickly tell me. This is 1's complement. What about step 2? Add 1. So 1 and 1. What is 1 1? 1 and 1, if I add, it is 2. Am I right? 2, it is 1 0. And meaning your sum is 1, your carry is 0. 1 and, sorry, sum is 1, carry is 0. 1 and then 1 2 3 1 1 1. Am I right? Am I right, guys? So you can even check with the help of your calculator. Yeah. Yeah. This is 2's complement. Okay. This is 2's complement of representing a negative number. Is it fine, guys? Okay.